Here is the idea this video will prove. 6G is not just a faster version of 5G. It is a different kind of network built for sensing, intelligence, extreme capacity, and global coverage. Most people assume 6G will follow the same pattern as earlier generations. 3G gave mobile internet, 4G made it practical, 5G made it fast. So the easy assumption is that 6G must simply be faster again. But that is exactly where the misunderstanding begins. 5G is impressive, but it still has three major limits. It does not reach everywhere affordably. It was not designed from the ground up for AI. And it cannot support every future use case we now want, including advanced sensing and massive machine connectivity. 5G still struggles in rural areas, remote regions, at sea, and in the air. Building dense tower networks and fiber backhaul is expensive and slow. That means large parts of the world remain difficult to serve well with terrestrial infrastructure alone. The architecture behind 5G was designed before AI became the dominant technology force it is today. AI can help optimize 5G, but it sits on top of the network rather than being built into the network itself. Modern networks are now expected to do more than connect phones. They need to support sensing, automation, trillions of devices, and real-time services across industries. That requires a new foundation, not just a speed upgrade. To understand 6G, focus on four core ideas. Terahertz spectrum increases speed and density. Reconfigurable intelligent surfaces reshape propagation. AI native architecture makes the network adaptive. And satellites extend coverage into a true global fabric. Every wireless system uses radio spectrum. Lower frequencies travel farther and penetrate obstacles better, but carry less data. Higher frequencies can carry more data, but they lose range and are easier to block. 4G mainly used spectrum below 3 GHz. 5G added millimeter wave between roughly 24 and 100 GHz. 6G research is now exploring terahertz bands above that, reaching into an entirely new operating range. Terahertz spectrum offers the possibility of extraordinary data rates, potentially up to 1 terabit per second in ideal conditions. That is the attraction. The trade-off is that these signals degrade quickly and work best across short distances. At terahertz frequencies, oxygen, water vapor, walls, and even small obstacles become serious problems. The signal range is often measured in meters, not kilometers, so 6G needs supporting technologies to make terahertz practical. Inside factories, hospitals, labs, transport hubs, and dense city zones, terahertz can make sense. These are environments where huge amounts of data need to move across short distances with extremely low delay and high reliability. A reconfigurable intelligent surface is easier to understand through analogy. A mirror reflects light toward where you want it to go. RIS does something similar for wireless signals by redirecting radio waves in controlled ways. These surfaces are built from engineered materials that can manipulate radio waves. Instead of letting signals scatter randomly, the surface can steer, focus, or reshape them so the signal arrives where it is needed most. RIS matters because it can help overcome one of the biggest weaknesses of high-frequency communication. If terahertz signals struggle with range and obstacles, a programmable environment can guide those signals through the space more intelligently. Imagine a room where the walls, ceiling, and even windows help direct wireless signals. In that model, the physical environment is no longer passive. It becomes an active component of the communication system. This leads to a larger idea called the programmable wireless environment. Instead of designing a network around a fixed building, engineers shape the environment itself so connectivity becomes more reliable, targeted, and efficient. In a factory, RIS can help keep sensors connected despite metal obstacles. In a hospital, it can support reliable indoor coverage room by room. In a stadium, it can help manage dense user demand by steering signals intelligently. 5G can use artificial intelligence as a tool, but 6G is being designed so intelligence is embedded into the network architecture itself. That is the difference between an add-on and a core operating principle. Think of an older car with digital features added later. Now compare that to a modern electric vehicle designed around software from the start. That is the difference between 5G plus AI and a truly AI-native 6G network. In an AI-native network, intelligence is built into routing, spectrum use, fault handling, security, and coordination between network elements. The network does not just carry traffic. It continuously learns and adapts. A 6G network should be able to study its own traffic patterns and adjust itself automatically. That means fewer manual interventions, better efficiency, and faster reactions to changing conditions. Instead of waiting for a crowd to overload the network, an AI-native system can anticipate demand and prepare capacity in advance. That is especially valuable for events, transportation hubs, and industrial environments. In 6G, the network could optimize service differently for each device based on context and usage. A medical sensor, a robot, and a video stream may all receive different handling at the same moment. AI-native architecture can also improve security. Networks may identify anomalies, isolate suspicious behavior, and respond far faster than purely manual systems can manage. A more intelligent network also raises real concerns. If a network predicts behavior and manages connectivity proactively, then privacy, transparency, and governance become just as important as technical performance. Another major 6G pillar is deeper integration of non-terrestrial networks. This includes satellites, aerial platforms, and other layers that extend connectivity beyond traditional ground infrastructure. The 6G vision combines three layers. The terrestrial layer uses towers and small cells. The aerial layer uses drones or high-altitude platforms. The space layer uses satellites, especially low Earth orbit systems. The goal is a device that can move across these layers automatically. Instead of thinking about terrestrial versus satellite coverage, the user simply remains connected as the network selects the best available path. This matters because it can bring reliable connectivity to ships, aircraft, remote regions, research stations, and rural industries. 6G aims for global continuity, not just isolated urban performance. The roadmap often points to commercial 6G around 2030. But commercial launch does not mean immediate mass adoption. Early deployments will likely appear first in selected cities and enterprise settings. Just as 5G took years to move from launch headlines to everyday availability, 6G will likely spread gradually. Broad consumer adoption is more realistic in the early to mid-2030s than right at launch. Even if 6G is not your next phone story, it matters now for long-term planning. Businesses, governments, infrastructure planners, and investors make decisions years before networks become mainstream. 6G matters across manufacturing, logistics, healthcare, transport, finance, and technology. You do not need to become an engineer, but understanding the shift helps you make better strategic decisions. So here is the takeaway. 6G is not just faster 5G. It combines terahertz capacity, intelligent environments, AI native control, and integrated satellite coverage to create a fundamentally different network model. If this helped you understand 6G more clearly, subscribe to Techtonic for more videos on 5G, 6G, AI networks, and the future of connectivity. The best questions from the comments often become future videos.